Hi, we are Team 25. Our project is unsupervised multi-domain image-to-image translation with a lightweight GAN. Compared to previous leading works, StarGAN V2 makes a great improvement on image translation in quality, diversity, and user satisfaction. However, one big issue about StarGAN V2 is that it is too heavy. The whole model has over 50 million of parameters. It requires over 60 gigamax to generate a 256 image. So it is challenging to be adopted in softwares or to be deployed on hardware devices with limited computational resources. So our project aims at developing a lightweight version of StarGAN without compromising much performance. To make the model smaller, we first need to compress the whole architecture. However, since the model is made smaller, its performance may drop. To solve this issue, we choose to use knowledge distillation. Another way to improve the model is from data augmentation. In this project, we apply adaptive data augmentation, or ADA, to improve our model. First, we will discuss model compression. Before that, we want to show you the basic architecture of StarGAN V2. It has four parts: generator, mapping network, style encoder, and discriminator. The generator contains convolutional residual blocks for encoding and decoding. We replace all the residual blocks for encoding with mobile residual blocks from the mobile net. This change will make the computation more efficient. We also reduce the channel width to 128. After compression, the number of parameters is reduced by 94%. The mapping network contains linear layers. We reduce the channel width the same as the generator. After compression, the number of parameters is reduced by about 93%. The style encoder also contains residual blocks for encoding. So we replace the blocks with the mobile residual blocks and reduce the channel width as before. The number of parameters is reduced by 98%. The last one is discriminator, which is not compressed. However, its architecture will be changed for knowledge distillation. We will discuss KD as well as object loss functions in the next section. As we mentioned before, the discriminator is modified for KD. Now, student and teacher send their labels to the discriminator. Then, we ask the discriminator to tell which labels are from student. In this case, it motivates the student to mimic the teacher. Ideally, the student can have results as good as teacher in the end. In practice, the distillation losses help the discriminator to evaluate the divergence between the student and the teacher. We list losses for generator, mapping network, and style encoder. Those losses will help each part of student mimic the teacher. ADA consists of 18 transformations. It uses augmentation probability value P to control the strength of augmentation. If P is high, the strength will be large. But why it is called adaptive? This is motivated by a very interesting observation. The figure on the right shows FID with respect to dataset size. P and a new value RT that is related to the losses from the discriminator. Look at the graph. We can find that when RT is 0.6, FID value is always low regardless of dataset size. So what we want is to make RT close to 0.6 by adjusting P automatically. The process is simple. We initialize P to be 0 and calculate RT to increment or decrement P based on the distance to 0.6. In this case, the strength of augmentation will be dynamic and guaranteed to be effective for training. Now we are done for the method section. Here is the final result of our model compared to the original one. From right to left, our model has 20 times fewer parameters than the original one. The max for computing an image has reduced by 5.7 times. The storage is reduced by over 10 times. Thus, we made a huge compression from the original model. On the other hand, the FID and LPIPS scores are really close to the original model on AFHQ, and even better on setup A. In general, the results have fulfilled our objective, and even better than what we expected. Here are some generated images from our model. The image quality and translation quality are still good after model compression and enhancement by KDE and ADA. In conclusion, and from our perspective, the impact of our project is to enable the adoption, utilization, and deployment for a SOTA model, which could never be put into the industry and production before. Now, the model is really lightweight. It is more convenient and much faster for transfer learning and other applications. It can also be easily imported as a plugin inside any image processing apps. And it can now be deployed on hardware devices and only need a little resource. That's all for our project. Thank you so much, and we hope you enjoy our presentation.